This is Mark Crescenzi's POLI 150H lesson accompanying Chapter 7 of Bruce Bueno de Mesquita's Principles of International Politics, 5th edition. Why do states have trouble cooperating? In Chapters 7 and 8, BDM considers how coordination and commitment problems arise from an anarchic international setting. Unlike in a domestic setting, in the international context there's no centralized authority to make decisions or enforce agreements. In this lesson, we'll look briefly at some of the reasons why this makes cooperation so difficult. Designing international organizations, or IOs, is one way to address collective action problems. Collective action problems affect multiple actors and therefore require joint efforts to solve. The nature of a collective action problem depends on the type of goods, products, or services that it seeks to address. According to BDM, these can vary across two dimensions. The first dimension is rivalry. Goods can either be rivalrous or non-rivalrous. Rival goods are goods that can be used up or depleted, like an offshore oil supply. When goods are rivalrous, they create distribution problems. How should states divide up a finite resource? In contrast, non-rivalrous goods are goods that can't be used up, like clean air and national defense. The second dimension is excludability. Goods that are excludable are limited to a set of people that contribute to the cost of providing the good. Non-excludable goods affect everyone, regardless of whether or not they have contributed. The harms or benefits other states derive from non-excludable goods are called negative or positive externalities. In Table 7.1, BDM outlines 4 types of goods in relation to these two dimensions: private goods, common pool resources, club goods, and public goods. Pause this video to brainstorm examples in your small group of goods or resources that would fit under these 4 types. Try to make your examples relevant to international relations. We're going to focus now on the collective action problem that emerges when benefits are non-excludable and non-rivalrous. Non-excludability creates an incentive for nations to free ride, to reap the benefit of a good without paying the costs. Unlike in domestic politics, where states have centralized authority to collect taxes and provide for domestic public goods, in the international system, there is no central authority. This causes a free rider problem, which can be illustrated with some basic game theory. For this first example, let's assume that each country contributes equally to some collective good. We'll represent the cost of contributing to a collective good as C. If the collected good is provided, everyone will have access to the non-excludable benefit, B. What expression would it represent the net value of the good? If you want to pause and work this out in your small group, feel free to. The net value of the good would be the benefits minus the costs, or B minus NC, with N indicating the number of countries who paid the cost. If everyone pays into the public good, the full benefit is produced, N over N times B. However, when N is large enough, states have an incentive to free ride. Why is this? Pause the video to discuss with your small group. If one government shirks responsibility, the benefit becomes N minus 1 over N times B. As N gets larger, N minus 1 over N gets closer and closer to 1. For instance, in N of 10 states in which 1 shirks will produce 0.9 B, but in N of 100 states in which 1 shirks will produce 0.99 B. In this free rider scenario, N minus 1 governments each pay C, and 1 government pays none of the cost. Therefore, BDM explains that states have an incentive to free ride when 1 over N times B is smaller than C. Pause the video and discuss this logic with your small group. The problem with non-excludable goods here is that there's no way to prevent a free rider from receiving the benefit without paying the cost. So how do we deal with international collective action problems? There's a large literature on this subject, and BDM discusses a variety of different organizational solutions in Chapters 7 and 8. As we've already established, one important component is the number of players involved in the game. When N is small, free riding is less likely. However, the overall worth of the benefit, B, is also likely to be smaller. There are some large international issues, like global warming, however, that require the involvement of lots of major states. When N is large, as we have seen, free riding becomes more likely. A second important component of a cooperation game is whether the game is repeated across time. In other words, how much do states care about the short term versus the long term? We'll look at repeated interactions by considering a bilateral setting, which involves two states. Consider a classic prisoner's dilemma situation. In the prisoner's dilemma scenario, we know that the optimal outcome is for both prisoners to cooperate, but the equilibrium outcome is for both players to defect. To illustrate this, let's consider an empirical example relevant to international relations. Nuclear arms races are often thought of as prisoner's dilemmas. Work with your small group to create a simple prisoner's dilemma game that reflects a nuclear arms buildup between two countries, A and B. Pause the video to complete the chart in a way that's consistent with prisoner's dilemma. How might this game change if it was played over time? Pause the video again to discuss in theory how this outcome could change if the two countries were playing the game repeatedly. Whether or not prisoners or states in a repeated interaction choose to cooperate depends on the shadow of the future, or how much players value future interactions. In mathematical terms, the value of future rewards can be represented by the discount rate, a delta symbol. Simply put, the discount rate is the reward in the current period is equal to the reward in the next period times the discount rate. If you were asked whether you'd like $100 now or $100 next week, chances are you'd probably want it now. But what if you had to choose between $100 now or $110 if you wait next week? What about $100 now or $150 next week? As the amount gets higher, you're more willing to wait. The point at which you're indifferent between the value today and the value in the next period helps you determine the discount rate. Hypothetically, if you were indifferent between $100 now and $110 next week, the discount rate would be 100 equals 100 times the discount rate, which is 0.909. If you are more interested in short-term games, your discount rate would be lower. What if your discount rate was 0.75 and the initial offer was 200? How much would you have to be offered in the next period in order to be willing to pass up on the $200 today? Pause the video to work out the math with your small group. 200 equals the rate tomorrow times 0.75. So you would have to be offered more than $266 in order to accept it. When games are played repeatedly forever, we can express the repeated sum of rewards as follows. This can be rewritten as R times 1 over 1 minus the discount rate. Let's return to the nuclear arms example. Consider a payoff matrix between country A and country B that is consistent with the prisoner's dilemma game. For simplicity's sake, we'll pretend that this is a bipolar system with two superpowers. They would both prefer sole dominance of the international system, which they value at $20 billion. They value a tie at $10 billion and a loss of superpower status at $0. We'll pretend it costs $5 billion to build a nuclear weapon, and each country can decide whether or not to build one nuclear weapon during each period of 1 year. From this information, work with your small group to fill out the chart. Pause the video until you have finished. Make sure you got these results. Feel free to pause the video again if you need to discuss the math with your group. Now let's consider an infinitely repeated interaction over time in which the discount rate is 0.95. In this scenario, if country A and country B both cooperate, they will cooperate forever after. Using the repeated sum equation, R times 1 over 1 minus the discount rate, what is the payoff of long-term cooperation? What is the payoff of long-term defection? Both countries building nukes in every round. Pause the video to calculate. If one country defects, pretend the trust is broken. In this situation, the payoff for the defecting country would be the initial reward for cheating, plus the infinitely repeated gains from defecting. Pause the video if you need to discuss math or discuss the implications of this outcome with your group. What if it's an election year in both countries, and the leaders care more about short-term gains? In this case, pretend the discount rate drops to 0.30. What are the payoffs now? Check your work. This is Mark Crescenzi's POLI 150.